So we're working with these partial sums. Is there a way to write it without writing the plus and the plus and the dot dot dot? Well, we could say let's write a summation sign there and maybe start at n equals 1 and go up to and do a sub n. But then where would we say we stop? According to this, if we wanted to do s sub 10, we would stop at 10, so we'd put a 10 here. But if we want to stop at n, we would put an n here. And that's actually pretty dangerous, seeing this upper end is the same as the letter we're trying to use that starts at 1 and goes to something. So having this and this be the same letter is a dangerous idea. It's going to be very confusing. If you write programs in any computer language, if you said for n equals 1 to n, depending on the computer language, some computers would just stop immediately, some would run on forever. So a better idea is to use a different letter to start at 1 and go up to something than we're using for the upper end of it. So we'd say maybe the sum, another letter we like to use is I, which I think of as standing for index. So we can say the sum up to n is I equals 1 through n of a sub I. And here we don't mean I like the square root of -1, like complex numbers. So this is saying I equals 1 and then 2 and then 3 dot 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 up to n. We're not saying I is the square root of -1 like for imaginary and complex numbers. So that's a good way of defining the partial sums. And then how about defining the sum up to infinity? Actually, we just wrote n there. We should say I now. Up to infinity. Well, like we did for integrals, we'll replace the infinity with something finite and then take that finite number up to infinity. So that will be the limit as n goes to infinity, the sum I equals 1 to n of a sub I. So this is similar to our idea of the limit as b goes to infinity, the integral of x equals something, doesn't really matter what, up to b f of x dx. Hopefully you can see the similarity in the notation there. And actually next we'll talk about similarities and differences between continuous notation and discrete notation. So let's make a table making analogies between what we do when x is continuous, it changes continuously, and when n is discrete, going 1, 2, 3, 4, 5, with nothing in between 2 and 3, for example. So in continuous territory, we have our function, and then we take the integral of it, which is the cumulative area so far, right? So we'll say cumulative area so far. And we had to, if we want to stop at x, then we can't use x to start at 0 or 1 or whatever. We have to use some other letter, so we often use t for that. And this is the cumulative area up to x so far. This is the function. You could also call it the integrand. It's the thing that we're integrating here. So what's the equivalent of this in the discrete world? We'd have a sub n, which is our sequence. And remember, you can also write it a sub a of n like that, which is a function of integers. So those two things are analogous. And then what's the discrete analogous thing for this sum? It's s sub n, the sum I equals 1 to n of a sub I, which is not the cumulative area so far really, it's the cumulative sum so far, or the partial sum, you could say. And then that's the thing we're studying. if stuff converges, well, should I say stuff or should I be more careful? If we see the integral converge, sometimes we start at 0, sometimes we start at 1. That's not really the important part here. So sometimes we'd say that's equal to L if the integral converges. What's an equivalent statement in discrete territory? We'd say the sum I equals 1 to infinity a sub I equals L. Or sometimes we lapse back into n equals 1 to infinity a sub n equals L. If the integral converges. Here would I say if the series converges or the sequence? Here I'm talking about the series, the infinite sum. So this is if the series converges. And an important thing to note, this is a mistake that people often make. If this integral converges, let's say the integral converges to like 29 or negative 500 million or something, there's no t or x left in the answer. It's just a single number. So if the integral converges, there's no t or x left in the answer. It should just be a single number. Here, if the sum converges, it should just be a single number like 29 or negative 50 million or whatever, and there should be no what left in the answer. There should be no I or n left in the answer. So if you've done a summation and you ended up with an I or an n left in there, something probably went wrong and we should go back and look at what happened. Alright, next we'll look at one of the biggest, most important series in this whole chapter called the geometric series.